Hi there, this is Mr. Lehan Teaches You Stuff, Grade 10 Optics Lesson 6, Ray Diagrams of Curved Mirrors. So when light rays parallel to the principal axis bounce off a concave mirror, they will all pass through the focal point. So the principal axis is basically the normal, in this case, the dotted line there. So if a light ray comes in parallel to that, it's going to bounce off the mirror and go right through the focal point, which is, in this case, that green dot right there. The point where the normal line reaches the mirror, or the principal axis line there, is called the vertex. So the vertex is just that spot right there. And the distance from the vertex to the focal point is the focal length. So the focal length is that distance in between those 2 points. Now the center of curvature is found 2 focal lengths away from the vertex. So if we go one more focal length away, that's the center of curvature. And what the center of curvature is basically if the mirror was a full circle instead of just a segment, like this, that yellow part there is the mirror. The center of curvature right there is the exact center of that circle. So it's the center around which the mirror is curved, basically. And that's the focal point halfway in between. When light rays reflect off a concave mirror, they will create an image that can be projected onto a screen at a specific point in space. So what I've done here is I've made a little setup. I've got a tiny little concave mirror, or it's a makeup mirror, and I've attached it to some Lego Duplo, and I've angled it in such a way that it should bounce off, the light should bounce off that mirror and then hit another pile of Lego where I've put a piece of paper as a screen. So what happens when you turn on the light is you get an upside down image of that light bulb. Pretty cool. Now, when an image is in front of the mirror, it's real. So if you put a screen at that point where the image is formed, it will be projected on the screen. So that's exactly what happened here. If the image is behind the mirror, it's virtual. And virtual images mean there can be no image projected onto a screen at that point. So make sure you keep in mind the difference between a virtual and a real image. Real images are anything in front of the mirror, basically. All right, now the main objective of creating a ray diagram is to figure out how far away the image is and how big that image will be. So the first thing we need to do is we draw a line parallel to the normal, or parallel to the principal axis, from the top of the real object over to the mirror. So once it hits the mirror, it's going to bounce off and it's going to go through the focal point. All right, next we need to draw a line from the top of the object through the focal point and onto the mirror. So it's going to go through that focal point and hit the mirror, and when it bounces off that mirror, it's going to travel parallel to the normal. Now where those 2 reflected rays intersect is the location of the top of the image. So there's our image right there. And it's important that it's always the 2 reflected rays. Wherever those reflected rays intersect is going to be where your image is. All right, now that we've done that, we can measure the image height and the image distance. So this right here is the image height. You just take a ruler and figure out how big that image is. And then to find the image distance, it's from the vertex all the way over to where your image is found. So that's the image distance. All right, we're going to go through several examples of what happens with a concave mirror. When the object is found more than 2 focal lengths away from the mirror, so we've got 1 focal length, 2 focal lengths, that would be the center of curvature. So when it's past the center of curvature, what happens? Well, let's see. We're going to draw a line, bounces off the mirror and goes through the focal point. Our next one's going to go through the focal point and then bounce off. And there's our image. And as you can see, the image is upside down and smaller than the object. So here's an example at a local museum where I've taken a picture of a concave mirror and I'm relatively far away, farther away than the center of curvature. And in this case, I am smaller and upside down. All right, when the object is found between 1 and 2 focal lengths away from the mirror, what happens? So there's one focal length, there's another focal length, so it's in between the center of curvature and the focal point. What will the image look like? Well, the line goes across there, hits the mirror, and bounces off going through the focal point. Our next one's going to go through the focal point, bounce off, and there's our image. It is much larger than the object and upside down still. So here I am in my real world example again, and as you can see, I've gotten much bigger as I move closer to that mirror, but I'm still upside down. Now, when the object is found exactly 1 focal length away from the mirror, what happens is the light will bounce off the mirror and go through the focal point, and then the other one will go straight through the focal point and then go on towards the mirror. But in this case, it doesn't hit the mirror because it's just going straight down. So you're not going to have reflected rays, and there's not going to be an image formed here. So when something's exactly 1 focal length away from the mirror, no image is formed. So here I am at exactly the focal point, or as close as I could get, inching back and forth. And as you can see, there's no real image formed here. You just see fingerprints of little kids all over the mirror. All right, now let's take a look at what happens when the object is less than 1 focal length away from the mirror. So here we have our light bulb, and you can see it's less than 1 focal length, right? It's in between the focal point and the vertex of the mirror. What we need to do first is what we usually do. We'll just draw a line across to the mirror and then through the focal point. Now we need to draw a line that goes from the top of the object through the focal point and then hits the mirror. But we can't do it in that order because otherwise we'd have to curve the line, right? We'd be going backwards. So in this case, we'll just rearrange the order of things. It's going to go through the focal point first and then hit the top of the object and then the mirror. So the line will go like that. All right, good. Now we have 2 reflected rays bouncing off the mirror, but we still have a bit of a problem because these 2 reflected rays will never meet each other, right? These 2 rays are getting farther and farther apart as they go. So we can't have them cross anywhere in front of the mirror. So what we'll do is we'll extend the lines, the reflected rays, behind the mirror. And now they cross. And where those 2 meet, we put our image. So when the object is less than 1 focal length away from the mirror, the image is larger than the object and it's right side up. So one everyday example of this would be makeup mirrors. If you look in a makeup mirror, generally your face is magnified. You look bigger. And that's because you hold it at less than 1 focal length away from your face. If you put the makeup mirror on the far side of the room, maybe 10, 20 feet away, and then you look at it, you'll see that you're actually upside down. So the image in this case is also a virtual image, which means it can't be projected onto a screen. And the reason why is because it's actually behind the mirror. So you can't have a projection of it behind the mirror because there's no light going behind the mirror, really. It's all bouncing off the mirror. So here I am looking at that mirror at the museum again, and I've gotten close enough to the mirror that I'm now right side up. All right, here's a quick video I took of that concave mirror at the museum, so you can see what it looks like as I walk towards the mirror and then back away from it again. All right, now we're going to take a look at convex mirrors. And convex mirrors are different than concave mirrors because the image is very consistently one thing. So we'll see what that one thing is. We'll start off the way we normally do. We draw a line from the top of the object over to the mirror. From here, it's supposed to go bounce off and go through the focal point. But the focal point is behind the mirror, so we'll just sort of draw an imaginary line behind the mirror, and then it continues on in front of the mirror as a real light ray. Next, we got to have one pass through the focal point and bounce off the mirror, so we'll just draw it straight to the focal point, and then we'll erase everything behind the mirror and draw it bouncing off parallel to the principal axis. Now these 2 reflected rays that we have are never going to meet, right? They're going farther and farther away from each other. So we're going to have to extend the reflected ray that we just drew that's parallel to the principal axis behind the mirror, just like that. So now our two reflected rays meet, and you'll see our image is smaller and it's right side up. And this is always the case in convex mirrors. So in convex mirrors, the image will always be smaller than the object, right side up, and they'll always be virtual. So it's behind the mirror all the time. So you can never project it onto a screen like I did in my kitchen with that light bulb and the Lego. So here's an example. This is just a security mirror. That's me in the bottom right taking a picture. And you'll see that everything is very tiny, and it's all right side up, and it's all virtual. And it doesn't matter how close or far away I get from that mirror, everything will always be right side up and tiny. All right, now let's look at calculating magnification. Magnification can be calculated by dividing the image height by the object height. So magnification equals HI divided by HO, or hi-ho. You know, like hi-ho, hi-ho, it's off to work we go. I would just remember that song. It's easier than remembering the equation. So we'll just do this like we normally do. There's our object, and it looks bigger. So let's calculate the magnification here. So we're going to look at the height of the image is 26 centimeters, and the height of our object is 12 centimeters. So magnification is HI divided by HO, height of the image divided by height of the object, which is going to be 26 centimeters divided by 12 centimeters, which works out to be 2.17. So we can say the image is 2.17 times larger than the object, or it's been magnified 2.17 times. Okay, we'll take a look at another example now, because magnification can also be calculated by dividing image distance by object distance. So magnification also equals Dido. And I don't know if there's a song about Dido, but just remember the hi-ho, hi-ho song and you should be all right. So in this case, we'll just draw in everything we need. There's our image. Let's calculate magnification now using the distance. So the image distance from the vertex there is 9 centimeters. The object distance is 38 centimeters. So we'll do DI divided by DO. That's 9 divided by 38. That gives us 0.24, which means our image is magnified 0.24 times. And since it's a decimal, since it's less than 1, that means that our image is actually smaller than our object. If it was greater than 1, then it would be bigger. Okay, so that's how you do magnification. And that is it for this video. So tune in to the next video when we have a look at refraction.